Good evening, everyone. Can you hear me and see the slides?
Yes, sir.
Yes,
Yeah,
sir.
okay. Today we'll be looking at hmm, tutorial on mass and energy balance. Okay. So we'll be doing some numericals. There are a lot of numericals here, so we won't be able to do everything today. So what I'll do is I'll just introduce you to how to do this mass and energy balance and how to tackle certain types of problems. And then the rest you have to do it on your own and you have to submit to me on Saturday. All right. This is for everyone who's doing the assessment. Let me tell you why this is helpful, because the activity, especially the people who've chosen the activity, this is very much related to the activity. Okay. So if you do this, you'll be able to do the activity also like uh, pretty well. All right. So let's proceed. So So today we'll be looking at mass and energy balance basics. I'll just tell you how to do it, and then we'll have an example. Then combustion and gasification, then electricity generation from biogas, and then boiler and superheater. The like I said, I'll be doing a few of them here, and then the rest you have to do. Okay. So what is mass and energy balance? So it is uh, you would have studied the law of conservation of mass, law of conservation of energy, right? Even in your school or even college, or but have you really thought about it, what it actually means? So basically, this is the first step in carrying out any, I mean, assessment of any process or any system. Okay. So let us say a species enters a system. So let's take, for example, let's say carbon, combustion of carbon. So what are the reactants here? Combustion of carbon alone.
Carbon and oxygen.
Yeah, oxygen or air. Okay. So
Yes.
carbon and oxygen enter the system. Okay. They undergo this transformation, and then out comes heat and carbon dioxide. Okay. So this is a very basic system over here. So now if you see the mass of carbon and the mass of oxygen that is entering. Okay. The mass of carbon dioxide that is exiting should be equal to the sum of the masses of C and O2. Did you get it? That is very simple. So whatever is entering the system, okay, the species may be different. The species undergoes a transformation. Okay. Outside you'll have, I mean, in the inlet you'll have different species. Outside you'll have different species. But then the mass should be conserved. That is, whatever is coming out, whatever is going in should come out. Okay. If not, there is some issue with the system. I mean, with your calculation, not with the system. Okay. So all the sum of the masses going in, right, should be equal to the masses coming out. And similarly, you have energy, where you have energy input to the system. It is transformed into other types of energy. Like let's say you have an heat input. Let's say a turbine, for example. So you have heat, that is or pressure energy, that is converted into mechanical energy. Okay. But those two should be equal, not exactly equal, but there are some losses also. So you have to consider the losses within the system. So energy is not destroyed there, energy is thus just lost. Okay. So if you take, let's say, a motor, for example, electrical energy is converted into mechanical energy. Okay. But some portion of the that energy is lost because of the friction, and that gets converted into heat in the windings and so on. Okay. So this is basically it. Okay. So you have the system, you have all these, inputs, outputs. So you have M1, M2, and that is going into the system, M3 and M4 coming out of the system. So this is mass balance, right? And the mass balance equation is simply M1 plus M2 equal to M3 plus M4. That's it. Okay, so this is very simple. Okay. Energy balance on the other hand, so you have the system, you have some two, let's say two types of energy going in or two streams of energy going into the system. Okay. And you're getting out some one stream of energy, let's say in form of heat or electricity, whatever it is, or work. Okay. And some heat or some energy is lost within the system. So the equation is simply E1 plus E2 minus the lost energy is equal to the output, that is E3. That's it. Any doubts in this?
No, sir.
Okay.
Sir, E loss is the same as would be the same as consumed energy, right?
Not consumed. What is consumed? You are just transforming one form to another, right? What do you
Okay.
mean by consumed? Because energy cannot be destroyed, right?
Yeah.
So even if you consume energy, you're basically consuming it to create some other form of energy, right? Or I mean, transform it to another form of energy.
Yes, sir. Okay.
So if you say, let's say, take motor for example, you are sending in electricity. The electricity is consumed. Energy is not consumed. Electricity is consumed to create mechanical energy. So electrical energy is consumed to create mechanical energy. So our output is work or mechanical energy. Okay. So if you look at it from an energy point of view, it is nothing is consumed or nothing is created. It's just transforming from one form of energy to another. That's it. Okay. So here's an example. So you have a diesel engine with an output of 1 megawatt. Okay. And it has an efficiency of 40%. So how much diesel is required to run this plant for 1 hour? So the diesel LHV is given. Okay. Can someone tell me how to approach this problem? I just need the approach. I don't want the answer. Okay, let me tell you this. So
Sir,
1 megawatt for 1 hour will give you 1 megawatt hour. So this is the energy output in the form of electricity. Yeah, now continue.
yeah, and based on the efficiency given, it is
Mhm.
not exact. We won't exactly get 1 megawatt hour actually.
No, I'm saying to produce 1 megawatt hour, how much, what is the diesel consumed?
Okay.
The output is
So
given to you,
if we give the system one kg of diesel, for example,
right?
um, the energy produced just a minute. Efficiency is 40%.
Yeah. Okay, you tell me in megajoules only. Forget the unit conversion and everything. Just tell me in megajoules. So you started with 1 kg of diesel. That is a very good starting point. You tell me now.
Yes.
Yeah.
So 1 kg of diesel will
Hmm.
release 45 megajoules of energy,
Yes, correct.
right? Um,
How does that translate to electricity? No, that's the question.
yes, megawatt per joules.
Forget unit conversion right now. Just tell me,
Yes,
okay, that 45 megajoule that you said, what form is it in? What is the form
it's
of
in the
energy?
form of heat.
Yes, exactly. Now, what does this system do? Like the diesel engine, what does it do?
Diesel engine, it generates heat.
I mean, no, you can see it here, right? The schematics right here.
Yes. Yes, based on the amount of diesel given, it will produce electricity with an efficiency of 50%.
That is correct. What does this engine do? I mean, that's what does it convert? I mean, it's a device for
It
conversion of
converts heat
energy.
energy to electrical energy.
That's it, right? So
Yes.
to do that, what is the cost? I mean, what is the cost we are paying to do that? Right?
Yes.
That is given here. Like we are losing. I mean, 60% of it is lost. Only
Yes.
whatever
60%
is
of the
going
heat.
in, only 40% is realized here. 60%
Yes.
is lost in some form or the other inside.
Yes.
Now tell me, now that this concept is clear, you tell me with 1 kg of diesel.
Okay.
I mean, don't do the calculations. I just want you to tell me what happens. Like, okay, you were telling me about 45 megajoule. Yeah, then what happens?
Yes. So it reacts with air. Air contains
Forget the
oxygen.
reaction. I just want the system. I mean, that's it. There's no reaction here, right? I mean,
Yeah.
I've not given about any reaction here, right?
Yes.
So you told me 45 megajoule of energy is released by 1 kg of diesel.
Yes.
Where is
But
that on the
out of the 45, only
right?
40% gets converted into
That's exactly
electricity.
what I'm asking. That's exactly what I'm
Okay.
asking.
Okay. Okay, sir.
Yes.
Yes. Um, so 40% of 45 is 45 into 0.4. So 18 megajoules
Yes.
is converted into electricity
Right.
for
So
1 kg of diesel given.
if you give 1 kg of diesel to the system,
Yes.
okay, which
Yes.
is equivalent to 45 megajoule, you get only 18 megajoule out because the efficiency is 40%. Did everyone
40%.
get this point?
Yes.
Did everyone get this or no? See, this is important from the point of view of the activity. Okay. So lower heating value or calorific value is just the amount of heat or amount of energy released upon combusting one or upon burning 1 kg of any fuel. So in this case, the lower heating value is 45 megajoule per kg. That means if you burn 1 kg of diesel, you get 45 megajoule of energy. You got the point, everyone?
Yes, sir.
Yeah. Okay. See, I'm getting responses only from the usual suspects. You know, I want the others also to participate. Otherwise, I'll just assume that you all got this, right? Okay. So that means 1 kg, if you are burning 1 kg of diesel, you'll get 45 megajoule of energy in the form of heat. What does a diesel engine do or diesel generator? It converts heat to electricity. But obviously there are some losses while doing that. So the efficiency is only 40%. So if you burn 1 kg of diesel, if you burn 1 kg of diesel, you are supposed to get 45 megajoules, but you get only 40% of this. What is 40% of 45?
18, sir.
18, sir.
18 megajoule. So at the inlet, you have given 45 megajoule, but at the outlet, you are getting only 18 megajoule. Okay, got it? Now, the second part of this question is that I have given you the output here. So for 1 kg of diesel, you are getting 18 megajoule of electricity outside. Okay. Now I have told you that I need 1 megawatt hour of electricity. So how many kgs of diesel do you need to burn to produce 1 megawatt hour of electricity? It's cross multiplication, but you need to convert either the megajoule to megawatt hour or megawatt hour to megajoule, whichever is convenient to you. So can you do that?
Yes, sir.
Yeah, please do it. Okay, convert, let's say, megawatt hour to megajoule or something. Okay, you can just use Google for that. Don't calculate it right now. So just type 1 megawatt hour to megajoule or something like that, and what's you get it? What is 1 megawatt hour and megajoules?
1 megawatt
3600.
hour is 3,600 megajoules.
Yeah, so 3600 megajoule. So 1 kg of diesel produces how much?
18 megajoules.
18 megajoule. So you need at the output 3600 megajoule. Okay. So how much diesel do you have to burn?
$200 kg, sir.
Yes, exactly. Okay. 200 kgs.
Yes.
So that's what is here. So I have 1 megawatt hour, which is 3600 megajoules. The energy available in diesel is 45 megajoule per kg. Okay. The energy balance equation is simply, okay, so you have here the mass of diesel times the LHV of diesel. That will give you how much is the energy input to the system. If you multiply it by the efficiency, that will give you the output energy that you get from the system. Okay, in whatever form. In this case, it is electricity. It could be whatever form. So from this, you can just calculate the mass of diesel using just this. Take this to the right-hand side. So E out divided by LHV of diesel times efficiency. So you get 200 kg. Okay. Any doubts? No? Okay. I'll move forward. So we spoke about the stoichiometric oxygen requirement for biomass in the previous lecture. So now you have to calculate the stoichiometric air requirement. So what is the formula, chemical formula, uh, the general formula for air that we are following as convention?
O2 plus N2.
How is that O2 plus N2? You have 1 mole of air and 1 mole of nitrogen in air.
No, 1 mole of air and
1 mole.
1 mole of oxygen and 3.76 moles of nitrogen.
Yeah. Yeah. So what is the chemical formula?
O2 plus 3.76 N2.
That's it.
Yes.
So instead of O2 in your equation in the previous lectures, you have done the equations, right? So instead of O2, you replace it with O2 plus 3.76 N2. Get it? Do you remember the equation in the from the previous I mean the chemical reaction, or you can just write it down. Write down the chemical reaction and balance it. Okay, let's do one thing. I'll just show you this thing because it's might be. So this was the equation, right? So if you have oxygen, this portion, actually this is wrong. I have to add a 3.76 into 1.05 into here. Okay, so that's okay. Whatever nitrogen goes in will come out and the product. It does not react in an ideal case. So instead of just O2, you have O2 plus 3.76 N2. That is the only difference. And on the right hand side, you have to add a plus 3.76 into 1.05 N2. That's okay. Now you can see that 1.05 moles of air, but this is not 1.05. This is 1.05 into 4.76. Okay. Because this is the total of this is 4.76 moles. Okay, but just for simplicity, I'm just telling you 1.05 moles of air are required to completely combust 1 mole of biomass. So in this case, 1.05 moles of air is 1.05 times, what is this? Oxygen 32 plus 3.76 times 28, which is the molar mass of nitrogen. Okay, so the total comes out to be 144.1 kg. Okay. So the molar mass of biomass, can you calculate from this? So you have 12 plus 1.4 plus 0.6 into 16. One atom of oxygen, which is 16 grams per mole. So you have 23 kilogram per kilomole. Okay. So how many kgs of air are required? So 144.1 divided by 23. So around 6.26 kgs of air are required to combust 1 mole of, 1 kg of biomass. Got it?
Yes, sir.
Yes.
Okay. So this one should be almost 5 moles of air because 1.05 times 4.76. But that's okay. This is for simplicity, I've written this as 1.05. Anyway, but you can do it this way. Okay. So you write down the equation and then 1.05 times, the molar mass of all of these O2 and N2, and calculate the total weight of the air. Okay, for 1 mole of biomass, and then the molar mass of biomass, which is 23 kilogram per kilomole based on this. So 12, carbon is 12, hydrogen is 1.4, oxygen is 0.6, 0.6 into 16. It is 1.4 into 1. Okay. So, okay. So you have 6.26 over here. Okay.
So could you
Now,
go back?
yeah.
Could you explain the units? It's not making sense because moles are where unit shows kg and then yeah.
Yeah, so over here, I am calculating this 1.05. In reality, it's 5 moles. I mean, forget that. Let's follow this 1.05 moles of air. How many kgs do these many moles of air contain? Do you get the point?
Yes.
See, if it is molar mass, means if it's the kg per mole or kg per kilomole. So if it is 1 mole or 1 kilomole, how many kgs does this 1 kilomole contain? So that's why this is in kg per kilomole. Okay. But here I'm calculating so many x moles of air, how many kgs of air does that correspond to? You got it?
Yes.
Okay.
Yeah.
So that's why here it's kg and this is kg per kilomole. Okay.
Yes.
Okay. So calculate the amount of air required for the gasification of biomass with the chemical formula CH1.4O.6. So this is the same biomass as you saw before. Now, if you remember the previous class, the equivalence ratio, okay, use that formula. You can refer to the previous lecture, use that formula to find out what is the actual amount of air that you need to give if you have to maintain this equivalence ratio. The stoichiometric air requirement is calculated from the previous step. So this is the stoichiometric air requirement, 6.26 kilograms. Got it? Now calculate how much is the actual amount of air that you need to give in. Okay. So for 1 kg of biomass, consider 1 kg of biomass. The equivalence ratio is 0.3. So tell me the steps first, or tell me what equivalence ratio is.
Equivalence ratio is the actual amount of gas provided divided by the stoichiometric requirement.
It's not gas provided, it's air or oxygen.
Air.
Okay.
Yes.
Technically, that's a gas, but yeah. See, air to fuel ratio of actual divided by air to fuel of stoichiometric.
Yes.
That is the equivalence ratio. Okay.
Yes.
So air to fuel actual is, so on the top you have what is the actual input of air. Okay. So see if I can, because I've not, okay, I'll just explain it right here. So air to fuel actual and air to fuel stoichiometric. So what is the actual amount of air? That is what we have to calculate. The actual amount of fuel, the amount of fuel I've told you to assume to be 1, right? 1 kg. Now the air to fuel stoichiometric, you've already calculated this ratio over here, which is 6.26.
6.26.
Okay. Now this is x divided by 1, or if you see here, air actual divided by 1 divided by 6.26 equals 0.3. Okay. So the actual air required is 1.88 kilograms. So if you have biomass and you want to carry out gasification, you don't want to completely combust the biomass. So you say you want to maintain an equivalence ratio of 0.3. So you know that for completely combusting 1 kg of biomass, you need 6.26 kgs of air. So to maintain 0.3 as your equivalence ratio, you just multiply by 0.3, you get 1.88 kgs of air. So you have 1 kg of biomass, 1.88 kgs of air that you need to give. So that so what will be the products here? Can you tell me in this case? If you have 1 kg of biomass, 1.88 kgs of air, what products will be formed?
Carbon monoxide,
Mhm.
carbon dioxide, water.
Are you sure? I mean,
It's
practically,
not-
yes. Practically, all of this will be formed, but I'm asking in an ideal scenario. What is happening here? If you give, you need 6.26 for complete combustion. You're
Yes.
giving
So
only
here
1.88.
gasification is happening.
Yeah. So gasification is happening. We are in gasification zone.
Yes.
So ideally, I'm asking, you're absolutely right. Even carbon dioxide and water will be formed, but ideally, what should be formed?
Hydrogen,
Yes, and
carbon monoxide.
that's it. So ideally, only these two should be formed. But in reality, we also get carbon dioxide. We also get a little bit of water from the moisture. We also get, I mean, if it is air, we get nitrogen. Okay.
Yes.
And if it's oxygen, pure oxygen, yeah, we don't get nitrogen. We also get carbon dioxide. Okay.
Yes.
Right. Now, so we spoke about the steam to biomass ratio. Do you remember this? Yesterday, just towards the
Yes.
end of the lecture, steam to biomass ratio. So it's as the name suggests, steam to biomass ratio is the moles of steam or kgs of steam given for per kg of biomass. Okay. So that is this is a parameter that you decide that I want to give like 2 kgs of steam per kg of biomass, something like that. Okay, this is something you decide based on the design of your plant. Okay. Now, the question asked here is uh, calculate the amount of oxygen and steam required for a gasifier consuming 200 kgs of biomass. At I have given you SBR in terms of moles. Okay. So what does this mean? SBR, steam to biomass ratio. So 2 moles of steam for 1 mole of biomass. That's what it means. Okay. So what you do is first you convert this into mass basis. Can you do that? Can you tell me what the answer is? This is the first step. Convert this into mass basis. How do you do that? Someone tell me.
So we don't know what the biomass contains, right?
You know, right? I mean, just the previous slide you have the molar mass of biomass. It's right here.
Okay, 23 kg.
Yeah. So you can, if you don't remember that, you can, I mean, anyway, the formula is given, you can just calculate it,
Okay, sir.
right? So what is the molar mass of steam? Anyone? Okay, what is the formula of steam? The chemical formula of steam.
H2O.
That's it. Yeah, 18 is right. 18 is absolutely right. The molar mass of biomass is, I mean, we just calculated a couple of slides earlier, that is 23. So now you calculate it. The numerator is steam, denominator is biomass. So steam to biomass ratio, remember that. Does no one have an answer yet? It's very simple. All you have to do is
1565.2.
huh?
1565.2.
How?
Um,
36 by 23. I mean, please give me an answer in decimals, not in fractions. No. You all have mobiles, calculators, everything. Just give me in decimal.
One 1.565.
1.565. Right? Yeah, that is true. 1.565. Yeah.
But it was mentioned the biomass, it was in the molar mass of biomass was mentioned in kg per kilomole.
Yeah. So this is also in mole, right? So if you take steam, what is the molar mass of steam? It is 18 kg per kilomole, right? It is either grams per mole or kilogram per kilomole.
Okay,
Both
okay.
are the same
Yes.
unit, no?
Yes, sir. Yes, sir. Yes, sir. Confused. Got confused there.
Okay. So now
Yes,
you
sir.
have this. So what is the steam to biomass ratio on mass basis? That is 1.56 kg of steam are used for 1 kg of biomass. So how much kg of steam are we giving in considering this example here?
1.56 into 200.
Yes.
313 kg.
312, 330. Okay, so that you have one part of the answer. The second part is oxygen, not air. To be absolutely sure of this, oxygen. So you have calculated what is the stoichiometric oxygen requirement?
1.05 into 32.
1.05 into, are you sure? Only that?
Into 32 into 0.3.
Are you sure?
Just a
What
minute.
is the stoichiometric requirement mean like? Yeah, you're right about the 1.05 part. Okay.
Yes.
Because 1.05 moles are required to, moles of oxygen are required
Oxygen are required
to
to
combust.
completely combust 1 kg of biomass.
Are you sure?
1 mole of biomass. Sorry.
It's 1 mole. Don't
Yes,
forget
1
that.
mole of biomass. Yes, sir.
So how many kgs of oxygen are required to combust 1 kg of biomass?
1.05 into 32 into 200.
How?
16 on the 16. O2. So 1.05 into 32 we have to do.
That's
That will
right.
be
So, okay, what will you get if you do 1.05 into 32?
33.66.
No. What is that? What is that parameter that you have calculated?
That is kg
Yeah, kg per
kilomole.
kg per kilomole of what?
Oxygen.
No, I mean, I'm asking you. Okay, let's come from the beginning. Like, okay, 1.05 is what?
1.05 moles of oxygen, O2,
Moles of oxygen for what?
to combust 1 mole of biomass.
Right. What is 1 mole of biomass?
1 mole of biomass is 23 kg per kilomole.
Right. And what is
Yes.
1.05 moles of oxygen?
33.6 kg per
Right.
kilomole. Okay, so 33.6 divided by 23 we have to do.
Yes. So that's the stoichiometric ratio. Don't forget
Yes.
that
yes,
it's
sir.
for 1 mole and not for 1 kg. Okay.
Yes,
So
sir.
what you have calculated is for 1 mole and not for 1 kg. So you have to divide it by 23, which is the molar mass of biomass. Okay.
Yes.
So
Yes.
you get stoichiometric oxygen requirement for 1 kg of biomass. Okay.
Yes.
Now you have an equivalence ratio of 0.3. Now what is so 1 kg of biomass? How much oxygen are you sending in?
1.46 kg.
Yes. So for 200 kgs,
200 kgs, 1.46 into 200, which is 292 kgs.
yeah, that's it. So did everyone get this? I'll explain it
Sir,
here.
sir, but
Yeah.
you mentioned there the ER is 0.3. So
Huh?
ER is 0.3.
Yeah, you've already done it, right? So you need oh sorry, wait.
Yeah, so we have to multiply
Multiply by
292 into
0.3.
0.3.
Multiply,
Yes, sir.
yeah. Okay. So I'll just come to that, okay?
Okay.
So this is the equation. This is the reaction that we wrote yesterday. So this is biomass, 1.05 O2. This is the balanced equation, right? Balanced reaction.
Yes.
Now, 1.05 moles of oxygen are required for complete combustion of 1 mole of biomass. So the molar mass of biomass is 23 kilogram per kilomole. So the stoichiometric oxygen requirement is 1.46 kg per kg of biomass. So you require 1.46 kg of oxygen to completely combust 1 kg of biomass. So if you have an equivalence ratio of 0.3, so what is the actual oxygen input? This multiplied by 0.3, which is 0.44 kilogram per kg of biomass. So you need, for complete combustion, you need 1.46, but then you are giving only 0.44 because your equivalence ratio is 0.3. Okay. So 0.44 times 200, which is a question, right? You need 200 kgs, right?
Yes.
So you need 87.6 kgs of oxygen.
Oxygen.
The steam to biomass ratio is 2 moles of steam per mole of biomass. We convert that into mass basis, which 2 into 18. 18 is the molar mass of steam, kg per kilomole. And 1 mole of biomass is 23 kilogram. So you have 1.56 kilogram for 1 kg of biomass. So for 200 kg of biomass input, we need 312 kgs of steam. Okay. Did everyone get this or any doubts? Anyone, please ask, because this is basically it. Okay. I mean, if you don't get this, you won't be able to do the activity, because this is the fundamental. Okay. So from this, you just build on for the activity. So please speak up if anyone if anyone did not get this, please tell me right now. Okay, I'll move on. This we'll do a little later. We'll come to this one. Okay, I'll tell you how to do these three. Okay, boiler and superheater mass and energy balance. Then you have domestic biogas digester and hot system gasification. All of these three I'll tell you how to do. You have to do it and give it to me on Saturday. It is mandatory for everyone attending the assessment. Okay. So just before the final assessment, I need your answers. All right. I'll guide you on how to do this. Okay. We'll start with oxy-steam gasification. So you have this diagram. Okay. So what happens in oxy-steam gasification is you have a reactor. So this is your reactor. The reactor, we are using some biomass. So the biomass has an input. I mean, we are inputting like 100 kg of biomass. Okay. And oh, sorry, this is not air, this is oxygen. Okay. So you have some amount of oxygen that is going in, some amount of steam that is going in. Okay. So you have biomass, you have oxygen, and you have steam. Those are your inputs. So what happens? It gets converted into syngas with a high amount of hydrogen, like we have seen yesterday. Okay. So if we have air as the oxidizer, we will have producer gas, which is high in nitrogen. In this case, we have syngas, which is high in hydrogen. Yeah, right. So now what happens? You have some ash and unburnt char that comes out from the bottom. Now, can someone tell me, take this system, this reactor, what is the mass balance of this reactor? Just establish the mass balance of this reactor.
So biomass plus oxygen plus steam is equal to wet syngas plus ash.
Exactly. So I've given like the stream names here, X, Y, and Z. So you need to know what X is, what Y is, what Z is, and you have steam also, right? Steam is also there. How do you find oxygen here? How do you find how much oxygen is going in?
We have the ER, which is 0.3.
Yes.
And we have the biomass input. So, and the molar mass of biomass is 23 kg per kilomole. And
Yes. And don't go into the details. I just need to know how you'll calculate it, just the steps.
okay. So we'll find the molar mass of both biomass and oxygen,
Right.
and divide the molar mass of oxygen by biomass, and we'll get the
Why?
well the
Why
stoichiometric
are
value
you doing that?
to get the stoichiometric value.
Yeah, but why molar mass? Molar mass of
oxygen. Yeah, molar mass of oxygen.
why do you need the molar mass of oxygen here?
Because we want to calculate how much oxygen is needed for 1 kg of biomass to burn.
Oh, okay. Okay, you're going from the reaction, right?
Yeah, yes, sir.
Okay, okay. Then you're right. Yeah. Yeah. So
Yes.
so what is the stoichiometric oxygen requirement? We just calculated in the previous slide. We calculated.
Yes, 1.05 moles.
Yeah. So how does that translate to mass?
Translates to mass as what is that? 1.05 into 32,
And
and divided by 23.
yes, right?
Yes.
Okay. So which is 1.46.
1.46.
So
So that is the
1.46 for 1
stoichiometric.
kg, 1 kg of biomass. You have
No,
100
sir.
kgs here.
No, sir. No, sir.
So what
We
is
have
the?
the ER also. We have ER also.
Oh, sorry.
So,
Yeah, you have the ER also.
so
So you multiply it by ER.
1.46 into 0.3.
Yeah. Which is?
1.46 into 0.3. We'll get 0.438
Yeah, 0.438, which is
per kg of biomass.
exactly. So for
So we'll
100
have to
kgs,
multiply it
how
by
much is
100.
this? Okay, oxygen.
43.8
Similarly,
kgs of oxygen.
Yeah, how do you calculate for the steam? Forget the boiler and superheater here. You leave this for now. Just focus on this stream. Okay. So you have steam going into the system.
Yes.
And I have given you the SBR.
Yes.
Okay, in moles on mole basis. We have just calculated. We know how to calculate. We know how to convert the mole into mass. Okay. So this is 2.566 moles of steam per mole of biomass. Convert that. So 1 mole is 18 kgs for steam and 23 kgs for biomass. Convert this into kgs. Okay. So 1 kg of biomass requires how many kgs of steam? That you will get multiply by 100. So you have the stream, you have oxygen, you have steam, and how do you calculate the ash?
Ash. So the ash can be calculated based on by subtracting Z from X plus
What is
steam
Z?
plus
How do you get Z?
We get Z from the equation.
How?
Like okay, this is syngas, right?
Yeah.
So syngas cannot be just CO2 and H2,
No.
which was in the previous case. Okay.
Do you know Z? Do you know how to calculate Z from this question? I mean, you can read the question, you can tell me, can you calculate Z in any way? Or can you calculate Y in any way from the question?
4% of biomass is removed as ash.
Exactly.
So 4% of 100 kg is 4 kg.
Exactly. So ash is 4 kg. This Y is 4 kg.
Yes.
You have oxygen, you have steam, you have ash. Can you calculate the wet syngas?
Yes.
How?
So 100
Mhm.
plus 43.8 oxygen plus steam is 2 kg per kg of biomass. So 2 into 100 is 200. 200 into wait, is 2.566. So 200 into 2.566.
200 how?
Because whatever no, yeah, it is 200 only.
Yeah.
200 kg of steam. Yes.
Yeah.
200 minus 4 kg. So
Yeah.
that is the syngas we get.
So
100.
you got the Z here, wet
Yes.
syngas.
Yes. Yes.
Now establish the mass balance for this system, which is, I mean, your knockout drum where you are removing the moisture. Well, this is the scrubber actually. You're removing the moisture. So your input is wet syngas. Your outputs
Yes.
are dry syngas and moisture.
Yes.
And I have given you what is the moisture content in the wet
25%.
syngas. So you can
25%.
calculate how much moisture is going out. What is the mass of this stream? So this Z minus A will give you the dry syngas B. Okay. So that is, I think, one part of the question. Okay.
254.8 kg of dry syngas.
Now you have established the mass balance here of these systems, right? For the reactor and the scrubbers. Okay. Now come to the boiler superheaters. Right. Now I have given you the heat energy required to produce steam is so much, 3643 kilojoule per kg. This is kg of steam. To produce 1 kg of steam, you need 3643 kilojoules. Okay. I have given you the diesel LHV. Okay. So you have to find out the amount of diesel. Can you do that?
Yes.
And I've also given you, I think the efficiency is given. Efficiency of this system is given. So you have the input. Okay.
Yes.
Input times the efficiency will give you the output. The energy I'm talking about, energy input times the efficiency will give you the output. Okay. And your output here is the energy in the steam, the heat in the steam. Okay. So which is this one. Right. So this is the heat contained within the steam. Okay. So this is your energy output for this system. What is the energy input? You have the diesel, 45 megajoule per kg times how many other kgs here. That's what you need to find out. You do it in the same way that we did for the diesel generator before. Use the same method here. Okay.
Yes.
Now, once you do that, you can calculate the emissions also. So you have C10H20. Write the balanced chemical equation for this for combustion of diesel. Okay. Now you know how much diesel is being burnt. So you have just calculated how much diesel is being burnt. All right. So, yeah, so let me tell you this. So this is for 1 kg of steam. So you know how much steam is going in. So based on that, you have to calculate the diesel. Now you know how much diesel is going in. Now substitute that in the equation, chemical equation. So for 1 mole, how much carbon dioxide is released, right? So once you do that, you will know that, okay, you can convert that into 1 kg. For 1 kg, what is the diesel carbon emissions? 1 kg of burning diesel, what is the carbon emission? Then you can say, okay, so this is for 1 kg. You know how many kgs are there, like how many kgs you are using here. Multiply that, you'll get the answer. Got it? Everyone? Yeah, I need this on Saturday from everyone who's participating. Okay.
Yes.
So if you have any doubts, please ask me, because so you're free to refer to anything. I don't mind that you're referring to some sources and everything. You can also refer to the class lectures and presentations. That's also fine. I just need the answer. I just want this calculation from you. Let's come to this one. This is very similar to the boiler and superheater you did just in the other example. So you are burning 100 kg of biomass with an ash content of 4% to produce. Yeah, with an ash content of 4% to produce superheated steam at 650 degrees Celsius. The water is at 225 degrees initially. So do you all know how to use the steam tables to find out the saturation, pressure, and temperature? Have you learned this yet?
No, sir.
Yeah, I mean, that's okay for you. I mean, I'm asking the mechanical students. Have we learned how to do it? Okay, not yet. Are you in third semester or? Okay, so let me put this on hold for now, okay, because we have not learned this, right? So I'll do one thing. I'll just cover this on that day only, on Saturday only, how to do this. I'll let you know. Okay. So we'll do this one. So you have decided to reduce fossil fuel usage at your home. So you need electricity, of course, for your home and heat. These are your major energy requirements. So you decide to install an anaerobic digestion unit for this purpose. Your power consumption is 3 kilowatt. You assume constant throughout the day. Okay. The thermal energy requirement for cooking is 1500 kilojoules per day. The gas stoves are 40% efficient. Estimate the amount of biomass required to fulfill your requirements for one day. Okay. And also estimate the stoichiometric air requirement for biogas. I have given you the composition of biogas here. All right. So how do you do this? So let's look at this diagram here. So from the biogas digester, you're getting the biogas. So one part of it is going to the engine to produce electricity. The other part is going to the gas stove to produce, to produce heat. Flue gas is the byproduct. Okay, forget the flue gas for now. So it's producing heat. Okay, so here you need 3 kilowatt output, and here you need 1500. Oh, this is 3 kilowatt hour per hour. So 3 into 24. You need 72 kilowatt hour of electricity over here and 1500 kilojoule of heat over here. Okay. I have not given you the engine efficiency. The engine efficiency you can assume to be 30%. The gas stove efficiency is 40%, which means to get 72 kilowatt hour over here, you need to give like 72 divided by 40%. That much amount of heat on top over here. Similarly, to produce 1500 kilojoule of heat over here, you need 1500 divided by 40%. So here it's 30%, sorry, and here 40%, right? Now you know how much is the heat requirement. Considering both, you convert both into kilojoules so that it's easy. Now considering both, you just add up both. You know what is the heat requirement from biogas. Okay. So now that you have that, you can calculate the lower heating value of biogas using this table. We have seen that a couple of days ago. We have done that in detail. If you remember that, or if you have any doubts, you can ask me right now how to do that. Okay. So now you know. So what is the LHV of diesel? I mean, sorry, LHV of biogas. So it is the amount of energy
Heat
released.
generated.
Yeah, heat generated for 1 kg of biogas. So over here you have calculated how much is the total heat required for your, electricity and heating requirements. Okay. And for 1 kg, how much heat is produced. So now you know, using those two numbers, you can calculate how much biogas is required. Do you get the point?
Yes.
Okay. Does everyone remember how to calculate the lower heating value of biogas here?
So the LHV is given already, right?
I mean, it's the LHV of methane only, right? You have to
Yeah.
calculate for biogas
Ah, biogas.
using the composition over here.
Yes.
Convert that into kgs. If you don't remember how to do that, please ask me. I'll tell you right now.
Yes, sir. Could you just repeat it once again?
Okay. So I've given you. So if you remember on that day, I told you that the LHV of methane is 50 megajoule per kg. From that, we calculated this in kilojoule per kilomole. Now I have given you directly in kilojoule per kilomole, so you don't have to do that calculation, that conversion first.
Yes.
Now there are two things that you need to do here. So you have the molar composition here, 55% methane, 45% carbon dioxide. On the right hand side, you have the kilojoule per kilomole. That is for 1 kilomole. If we have 1 kilomole of methane, you have so much kilojoules. And if you have 1 kilomole of carbon dioxide, you have so much kilojoules. In reality, though, you don't have 1 kilomole in biogas. You have only 0.55 kilomole, 55%, right? If you take 1 kilomole of biogas, you have 0.55 kilomoles of methane and 0.45 kilomoles of carbon dioxide. So you multiply these two, add them. So 0.55 times this number, 0.45 times 0, add both numbers, you will get the final LHV in kilojoule per kilomole of biogas. Okay. Now you have to convert that kilomole into kgs. How do you do that? So you need the molar mass of biogas. So how to do that? So again, 0.55 and 0.45 you have. So if you have 1 kilomole of methane, you have 16 kgs. If you have 1 kilomole of carbon dioxide, you have 44 kg. But here you don't have 1 kilomole, you have only 0.55. You have only 0.45. So 0.55 times 16.04 plus 0.45 times 44.01. That is your total. That is the biogas molar mass. Okay. So you just do kind of like some product like this times this times this, add them both. This times this times this, add them both. Now you have the kilojoule per kilomole. You have the kilogram per kilomole. Now you need kilojoule per kilogram. You just have to, whatever number you got here, divided by this. That will give you the LHV in kilojoule per kg. Okay. Got it? If you don't get it, please ask me.
Yes, sir. Got it.
Is there anyone who didn't get it? I need some form of communication. Otherwise, I'm going to think you all got it and that you will be able to do this in the activity. Okay.
Yes. Sir, is the value 15,411.14 kilojoule per kg?
I've calculated, is it? I haven't
Yeah.
calculated. I need to check.
Oh, it's okay, sir.
Okay.
Yes, sir.
I haven't calculated it. It calculated somewhere, some time before. I don't remember that.
Okay, sir.
Wait 1 second. I'll just calculate right now. You got how much?
15,411, sir.
Yeah, that's right.
Okay. Thank you, sir.
Okay. So 15,411 kilojoule per kg. That is the
kg. Yes.
yeah. This is kilojoule per kg. That is the
LHV,
LHV of biogas.
biogas.
So from here, you know how much kilojoules you need. You have calculated it just now.
Yes.
Okay.
Yes.
So for 1 kg of if you burn 1 kg of biogas, how much kilojoules? How many kilojoules are produced? You know that. So calculate how many kgs are required. That's it.
Okay.
Okay. Now you
Yes.
can also estimate the second portion is the estimation of stoichiometric air requirement for biogas.
So air is
using
mentioned here, not oxygen.
not oxygen, air requirement. That is the second part. You're not using it for anything, but I'm just asking you to estimate that. You have the molar
Okay.
composition. So you know the chemical formula of biogas using this. You can write it down as 0.55 CH4 plus 0.45 CO2. That's it.
Okay.
Now try to balance the equation.
So the CO2 is not reacting with anything. So it is just given out into the atmosphere.
Yeah, kind of. That is true. But then you have to consider it for the balance.
Yes, sir. Yes, sir.
In the previous case, in the case of biomass, you had only one carbon atom on the left-hand side. But here you
Yes.
have 0.55 CH4 plus 0.45 CO2. So you have 1 mole of carbon. On the
Yes.
right, you will have 1 mole of carbon. That has to be reflected here.
Yes,
So
sir.
basically, you cannot just ignore CO2. You can't just say, okay, I'll remove CO2. I'll just put it on the right-hand side. That's not how it works,
Okay.
right?
Yes,
So
sir.
because the CH4 getting combusted is also producing CO2. That is additional CO2.
Correct.
Okay. So I need you to do this domestic biogas digester and oxy-steam gasification. The steam part, I mean, this one I'll pause it for now because you guys haven't learned how to do, the steam tables and stuff. So I'll pause it for now. So this one, domestic biogas digester and oxy-steam gasification, I need the answers individually for everyone who's participating on that day, on Saturday. So as you're entering, you can just submit it and then, right, it's mandatory for everyone. Got it?
Yes.
And doing this will help you in your activity because it's literally, this is one of the steps in the activity. Okay. And everyone can, you can use the lectures, of course, but I would expect you to, go through the lectures thoroughly because the activity will have a reference to some concepts within the lecture. Okay. So any doubts in this? In what we did today? Any doubts at all? Please tell me.
Sir, in this oxy-steam question,
Yeah.
you mentioned at the end, what was that? Like the second part of the problem you explained, right, sir?
Right.
Like how much diesel is required.
Yeah.
Could you explain that part once?
Okay. So the energy required to produce steam is so much.
Okay, to produce 1 kg of steam, we
1
require
kg of steam,
3,600.
rather you take it this way. 1 kg of steam contains 3,643 kilojoules of energy.
Energy. Okay.
It is in superheated form. So the heat content of the steam is 3,643 kilojoules.
Okay, sir.
Okay. Now you know the output. The energy output you know here. So this is per kg. So now you have already calculated how many kgs of steam are required. So you can calculate total kilojoules required. Okay. Or total
Yes.
kilojoules over here for this stream. Okay.
Yes.
Now I have given you the 45 megajoule per kg. So for diesel, if you burn 1 kg of diesel, you're producing 45 megajoule. That is the input here. Okay.
Okay.
That is the input. The efficiency is 50%. So here 50% of the energy is lost.
Okay.
Got it? So
Yes,
if you go reverse here, so you know how much energy is required, divided by 50% or multiply by 2, you will get this.
Okay.
How
The
much
required
energy is
diesel.
required from diesel? How much energy is
Yes.
required at the input of the boiler and superheater?
Yes.
So that is in energy form, in kilojoules.
Yes.
Now you have this. So 1 kg produces 45,000 kilojoules.
Okay.
So how many kgs of steam are required?
And diesel is required. Yes.
Yes. And the third part is C10H20. You write the balanced chemical equation. Okay. Find out how
Okay.
much carbon dioxide is produced for 1 kg of diesel. And you have just found out how many kgs of diesel are required. So find out what is the carbon emission of burning diesel for this.
Okay. Yes, sir. Got it.
Got it?
Yes, sir.
Okay. Any more doubts? Okay. So I just need to change this one. I'll change that and I'll send it to you in the group along with instructions. I mean that you need to do these two questions and send it across to me, or you know, you could either send it across to my WhatsApp or mail or whatever, or you could even hand it over to me as hard copy on Saturday. That's okay. But the deadline for this is Saturday. Okay. All right. So thank you all for joining. Okay. So I'll see you tomorrow at 7.
Yes. Thank you, sir.
All right. Okay.